May 1943. North Atlantic, western approaches. German U-boat strength reached its peak. 240 operational submarines, 118 at sea. Yet that same month, the U-boat arm suffered catastrophic losses. 41 boats destroyed, roughly 25% of all active submarines. Allied merchant losses fell to 34 ships, totaling 134,000 tons, less than half the peak losses of mid-1942. German Naval Command expected technical advances would keep interception rates manageable. Instead, convoys like ONS-5 and SC-130 saw escort groups detect, hold, and destroy attacking U-boats at ranges previously considered unattainable. Post-war analyses highlight radar and code breaking. But buried in Division 6, technical reports lies a quieter change. Retuned hydrophone filters and disciplined gainwriting pulled weak submarine signatures from Atlantic noise, extending effective sonar range by thousands of yards. This documentary asks, how much of Black May's collapse rests on how Allied engineers learned to listen? June 1942. North Atlantic convoy routes, British Admiralty, London. An operations officer spreads monthly loss tables across a wooden desk in the Admiralty's war room. The numbers tell a brutal story. June 1942. 124 Allied ships sunk worldwide in a single month. Over 6 million gross registered tons of Allied shipping lost that year, the worst 12 months of the war. The columns are organized by convoy designation, date, position, and cause. Most entries carry the same notation. Torpedoed by U-boat. Britain's survival depends entirely on Atlantic convoys. Food, fuel, industrial materials, American war goods, all must cross 3,000 miles of ocean where German submarines hunt in packs. The scale of the battle is already historic. By war's end, 3,500 merchant ships and 175 warships will be lost to U-boats. 783 U-boats will be destroyed. 72,000 Allied seamen and 30,000 German submariners will die in the cold Atlantic. The strategic arithmetic is simple and terrifying. If convoy losses continue at this rate, Britain cannot sustain the war. Every ship that fails to arrive means less food in rations, fewer shells at the front, diminished industrial capacity. Churchill will later write that the only thing that ever really frightened me during the war was the U-boat peril. The officer reviews the escort arrangements. By mid-1942, most convoys have dedicated escort groups, destroyers, corvettes, frigates equipped with ASW echo-ranging sonar. British sets carry designations like Type 123 and Type 128 ASW. American escorts mount echo-ranging gear, designated JK, JP, or early 692 series sonars. Simple hydrophones provide passive listening capability. Depth. Charges provide the killing blow. On paper, the technology appears adequate. ASW works by transmitting acoustic pulses underwater and listening for echoes reflected from submarine hulls. Typical effective detection ranges run 1,500 to 3,000 yards under good conditions, calm seas, moderate speeds. Hydrophones allow passive detection of submarine machinery and propeller noise at similar or occasionally greater ranges. But operational reports tell a different story. Escorts equipped with functioning sonar often report no contact before or after U-boat attacks penetrate convoy screens. Submarines slip through escort cordons, fire torpedoes from close range, and escape before depth charges arrive. Post-attack searches frequently yield nothing despite thorough echo-ranging sweeps. The gap between design performance and combat reality grows wider each month. Pre-war assumptions held that ASW combined with convoy tactics would reduce submarines to nuisance status. Submarines would be forced to operate submerged at slow speeds where sonar would detect them at safe distances. Reality proves far harsher. In 1942 alone, 1,322 Allied merchant ships fall to U-boat torpedoes. Many escorts report detecting U-boats only after torpedoes strike or when periscopes are visually sighted, if at all. The officer marks another notation on the chart. Detection ranges fall sharply with speed and sea state. Ship self-noise, propellers, machinery, hull vibration overwhelms hydrophone reception above 10 or 12 knots. Atlantic weather further degrades performance. Moderate seas and wind generate underwater noise that masks faint echoes and tonal signatures. What works at 5 knots in calm water becomes nearly useless at convoy speed in typical North Atlantic conditions. By early 1943, the Royal Navy and United States Navy deploy more escorts with better training and improved tactics. Yet adding more ships with the same equipment produces diminishing returns. The fundamental limitation is becoming clear, not the presence of sonar, but how it is used and what physics allows operators to hear through Atlantic noise. A statistical paradox is emerging. U-boat numbers and Allied sinkings both climb through 1942 and early 1943. Yet within 3 months, the same escort types will begin destroying submarines at unprecedented rates, without any radical new weapon entering widespread service. The convoys that survive Black May will carry the same destroyers and corvettes that struggled through the previous winter. But something in those black boxes, labeled ASW and QHB, will have changed. 1941 through 1943. Washington, District of Columbia. New York, Cambridge, Massachusetts, San Diego, California. A contract file at the Office of Scientific Research and Development sits on a desk, stamped with routing instructions. Division 6, Underwater Sound. The distribution list names institutions that will reshape undersea warfare: Columbia University, Harvard University, University of California, Naval Research Laboratory. Naval officers traditionally view sonar as equipment acquired from industrial contractors, hardware installed, operators trained, doctrine written. The Office of Scientific Research and Development sees something different: a system problem requiring coordinated design of transducers, amplifiers, filters, ambient noise characterization, and operator training. OSRD Director Vannevar Bush and National Defense Research Committee Chairman James Conant organize wartime science as a networked effort linking universities, Navy laboratories, and industry. On June 28, 1941, as U-boat attacks escalate, OSRD establishes Division 6 specifically for underwater sound research. 3 university-based laboratories form the core of the effort. Columbia University Division of War Research operates from New York, focusing on passive detection devices, array processing, and theoretical acoustics. Harvard Underwater Sound Laboratory, established under physicist Frederick V. Hunt, concentrates on magnetostriction transducers, active sonar design, and operator training aids. University of California Division of War Research in San Diego conducts oceanographic measurements, ambient noise surveys, and operates test ranges. The mandates are explicit and practical. Develop directional listening systems, characterize ambient noise spectra in operational sea areas. Improve sonar receiver performance through filtering and automatic gain control. The emphasis gradually shifts from simple broadband amplification to carefully shaped frequency response targeting U-boat acoustic signatures. Naval Research Laboratory provides the Navy's in-house research capability, interfacing academic work with fleet requirements. New London facilities, home to submarine and anti-submarine warfare schools, serve as the proving ground where laboratory concepts meet operational reality. Bell Telephone Laboratories contributes electronics expertise, filters, automatic gain circuits, advanced amplifier designs. The network functions as a unified research machine. Engineers at Columbia develop array theory. colleagues at Harvard build prototype transducers. California teams measure actual ocean noise under combat conditions. NRL translates findings into equipment specifications. Bell Labs designs production circuits. New London trains operators to use the results. By 1943, almost every American and many British anti-submarine warfare sets contained circuitry or design decisions rooted in Division 6 contracts. The coordination creates an institutional memory. When one laboratory discovers a better filter configuration, the finding propagates through technical reports, contract reviews, and inter-laboratory meetings. What begins as a single test result at a San Diego range becomes a standard design feature in production sonar sets within months. Problems identified in convoy after-action reports flow back through Navy channels to university labs, closing the feedback loop. Post-war documentation will make the scale clear. Summary technical reports prepared by Columbia's Summary Reports Group under OSRD contract will fill dozens of volumes, covering everything from transducer metallurgy to auditory masking psychology. These reports represent previously classified wartime work, systematically compiled for future reference. Volume 14 alone, Underwater Sound Equipment, Listening Systems, runs hundreds of pages describing hydrophone arrays, amplifier schematics, filter networks, and operational procedures. The engineers and physicists in this network rarely command ships or fire weapons. Many never go to sea. Yet their decisions on filter cutoff frequencies, gain laws, and frequency response curves will influence the survival of entire convoys. A circuit designer at Bell Labs choosing resistor values for a high-pass filter cannot know which specific convoy his work will save. But by summer 1943, his choices will be deployed on escorts hunting U-boats across the North Atlantic. This distributed, coordinated effort represents something new in naval warfare: the systematic application of scientific method to combat systems under active use. Not a single genius producing a breakthrough, but hundreds of specialists refining details until marginal improvements accumulate into measurable tactical advantage. The Manhattan Project receives more attention and larger budgets. Division 6's underwater sound program operates more quietly with less drama. But its products will be deployed sooner and will directly affect battle outcomes within months rather than years. Almost none of these engineers will achieve public recognition. Their work remains classified for years after the war. When historians later write about Black May and the defeat of the U-boats, radar and code-breaking dominate the narrative. The filter networks and gain-writing procedures refined in university laboratories receive passing mention at best. Yet without those carefully tuned receivers, much else would have failed to matter. 1946, reporting on work from 1942 through 1945. Publication of NDRC Summary Technical Report, Division 6, Volume 14, New York and Washington. A post-war Navy officer opens the bound volume titled Underwater Sound Equipment, Listening Systems. The cover is utilitarian, no classification stamps now, just technical documentation. The table of contents runs several pages: magnetostriction hydrophones, JP listening gear, amplifier design, frequency response curves, sections on filter networks, appendices detailing circuit schematics. The report represents systematic documentation of what was learned while the battle still raged. Prepared by the ETA Summary Reports Group at Columbia University. Division of War Research under contract OEMs 1131, it compiles previously classified technical work into a permanent reference. Fleet operators saw new sonar sets appearing on their ships. This document explains what changed inside those gray boxes. Fleet mindset during the war focused on obvious hardware, more powerful pings, longer echo ranges, better bearing accuracy. The Summary Technical Report narrative reveals a different emphasis. The primary effort in late war years centered on refining receiver chains, hydrophones, filters, gain controls, operator interfaces, rather than transmit power. Improving what happened after the echo returned proved more important than increasing the strength of the outgoing pulse. The technical evolution documented in Volume 14 shows progression from simple systems to sophisticated receivers. Early war hydrophones consisted of single or small arrays with relatively uneven frequency response. Early amplifiers provided straightforward gain across a broad frequency band. Everything got louder together, signal and noise alike. Operator controls remained basic: volume, bearing selector, perhaps a coarse frequency switch. By mid-war, the approach had fundamentally changed. Volume 14 describes multi-element hydrophone arrays with improved directivity, allowing operators to determine bearing more precisely. More significantly, receiver circuits incorporated cascaded high-pass filters. The document specifies 4 high-pass filters in one standard listening system, designed to strip low-frequency wave noise while preserving higher-frequency submarine signatures. Bandpass sections allowed emphasizing specific frequency ranges where propeller blade rate harmonics and machinery tones were prominent. Scale expander potentiometers and automatic volume control circuits compressed dynamic range, helping operators distinguish faint, continuous signals from intermittent noise bursts. The report notes persistent acknowledgement that full optimization of arrays and electronics was not achieved by 1945. The war ended with work still ongoing, but key gains were already in fleet service, installed on escorts fighting the Battle of the Atlantic through 1943 and 1944. The technical language is precise and unemotional. A section on frequency response specifies uniform response over the range 0.2 to 10 kilocycles. Circuit diagrams show resistor and capacitor values for filter sections. Performance curves plot signal-to-noise ratio against frequency for various filter configurations. The tone remains that of engineering documentation: problems identified, solutions tested, results measured, improvements implemented. Yet embedded in these technical details is the answer to an operational question that haunted convoy commanders. Why did detection ranges vary so dramatically with conditions? Why could one escort hold sonar contact through a running battle while another, identically equipped, lost contact in the first minutes? The summary technical report provides the answer. Receiver configuration and operator technique materially affected what could be heard. Two ships with identical transducers and transmitters could achieve vastly different detection performance based on what happened in the receive chain. The document carefully notes that listening system design seeks to raise the signal above the ambient noise, and that this was largely a matter of frequency selection and gain control. In other words, the decisive contest occurred not in the water, where physics determined sound propagation, but in the electronic circuits that processed returning signals. A few decibels of improved signal-to-noise ratio, achieved through better filtering and gain discipline, could mean the difference between detecting a U-boat at 2,000 yards or missing it entirely until torpedoes were in the water. When escort captains reported better contacts in 1943, how many realized the decisive change was not a new weapon, but a retuned amplifier hidden behind familiar dials? The summary technical report documents the reality. Marginal improvements in receiver performance, multiplied across hundreds of ships and thousands of convoy actions, accumulating into strategic significance. Not drama, not breakthrough. Just careful engineering applied systematically until the numbers changed. 1942 through 1944. University of California Division of War Research Field Stations, Pacific and Atlantic Test Areas. Report dated September 26, 1944. Researchers lower hydrophones over the side of a small vessel, carefully logging ambient noise levels while wind speed and wave height are recorded. The measurements accumulate. Noise spectra at different frequencies, correlated with surface conditions, water depth, biological activity. The ocean, it turns out, is not a quiet medium broken only by intentional signals. It roars with continuous background noise. Early sonar thinking assumed the underwater environment was acoustically clean. Ships and submarines would stand out clearly against a relatively silent background. Operational experience quickly demonstrated otherwise. Wind-generated surface noise, ship self-noise from propellers and machinery, biological sources, snapping shrimp, vocalizing marine mammals, create continuous background levels that often sit only a few decibels below submarine acoustic signatures. The UCDWR teams, led by physicist Vern O. Knudsen and colleagues R. S. Alford and J. W. Emling, systematically characterize this noise. Report number 3, Ambient Noise, from the series Survey of Underwater Sound, summarizes data available to March 15, 1944. The findings produce empirical plots that will become known as the Knudsen curves, noise level versus frequency for different sea states. The quantitative results prove critical for sonar design. In the 1 to 50 kHz band, the range where World War II sonars operate, noise level increases with wind speed and wave height. For any given wind speed, noise level generally decreases with increasing frequency. But the relationship is complex. Certain frequency bands show less noise variation with sea state. U-boat propeller blade rate frequencies and machinery tones occupy overlapping bands. The engineering challenge becomes clear. Identify frequency windows where submarine signatures can stand above ambient noise under realistic Atlantic conditions. The measurements reveal why broadband amplification fails. Simply increasing gain uniformly across all frequencies raises both signal and noise. The signal-to-noise ratio remains constant. Practical detection range stays unchanged once ambient noise dominates, which happens quickly in any weather above flat calm. A submarine's acoustic signature might be strong enough to detect at 5,000 yards in theory, but if ambient noise in the same frequency band sits only 3 decibels below that signature, detection range collapses to a few hundred yards once typical sea state is factored in. The UCDWR data provides engineers with hard numbers. A sea state 3, rough to moderate seas, common in the North Atlantic, adds 3 to 6 decibels of extra noise in key frequency bands compared to calm conditions. That difference is enormous. According to standard sonar range equations, every 3 decibels of lost signal-to-noise ratio roughly halves detection range. Going from calm seas to typical Atlantic weather can reduce effective sonar range by 50 to 75%. No amount of transmitter power compensates for that loss at the receiver. The University of California teams compile their findings into design tables circulated to equipment developers. Now engineers know which frequency bands can carry useful information under realistic conditions. They know where to place filter cutoffs to maximize signal recovery while minimizing noise. They understand that listening in the wrong frequency band is worse than not listening at all. It simply fills operators' headphones with useless noise, masking the faint signals they need to hear. The ambient noise work connects directly to filter design at Columbia, Harvard, and Naval Research Laboratory. Those laboratories now have quantitative targets. A filter network must preserve frequencies where U-boat signatures are strongest while attenuating bands dominated by wind noise or biological sources. Automatic gain control must respond quickly enough to suppress transient noise bursts without losing weak, continuous submarine tones. The entire receiver chain must be optimized against measured ocean noise, not against theoretical quiet water assumptions. The operational impact is stark. If the ocean adds 3 to 6 decibels of extra noise under common weather conditions, and measurements confirm it does, Then recovering that margin in the receiver through filtering and gain discipline becomes the only practical solution. Increasing transmitter power helps, but power is expensive, space-consuming, and limited by available electricity aboard escorts. Improving receiver design is cheap, compact, and can be retrofitted to existing equipment. The physics of the ocean determines what is possible. The electronics determine what is achieved. The Knudsen curves represent months of tedious measurement work, lowering hydrophones, recording spectra, correlating data, checking results. The researchers receive no medals. Their work appears in technical reports circulated among specialists. Yet these curves fundamentally reshape sonar design. From late 1942 onward, every significant sonar receiver development in the Allied navies incorporates ocean noise data. The engineers who design filter stacks and gain laws now work from measurements, not guesses. That transition from assumption to data marks the moment when sonar begins to become effective under combat conditions. 1943 through 1944. Columbia University Division of War Research, New York and Fort Trumbull. Naval Research Laboratory, Washington, Bell Telephone Laboratories, New Jersey. An engineer compares oscilloscope traces displayed side by side. The first trace shows broadband listening output, a chaotic jumble of high-amplitude noise spikes with no discernible pattern. The second trace displays the same hydrophone signal after passing through a prototype filter network. The difference is dramatic. The noise floor drops. A faint periodic signal emerges from the background, the rhythmic signature of a submarine's propeller now clearly visible. Fleet officers equate better sonar with more powerful transmitters, louder pings, stronger echoes, longer maximum range. Laboratory data tells a different story. Small changes in received filtering can produce similar or better detection gains without touching the projector. The oscilloscope traces provide visual proof. Adding the right filter transforms unintelligible noise into a trackable contact. Division 6 laboratories develop filter stacks based on both theory and measurement. Cascaded high-pass filters strip low-frequency wave noise generated by surface action. Optional bandpass filters center around frequencies where propeller blade rate harmonics and machinery noise are prominent, typically several kilohertz for World War II submarines. Switchable configurations allow operators to select modes optimized for different conditions. Quiet sea, rough sea, or machinery tone settings, each with different filter characteristics. The technical implementation draws directly on Volume 14 documentation. Standard listening system circuits incorporate 4 or more high-pass filter sections in series, each designed to attenuate frequencies below a specific cutoff while passing higher frequencies. Additional bandpass stages can be switched in to emphasize narrow frequency ranges. The goal is a receiver frequency response carefully shaped to match the problem. Maximize sensitivity where submarine signatures appear. Minimize gain where only noise exists. Bell Telephone Laboratories contributes expertise in electronics design. Their engineers develop stable, reliable filter circuits that maintain performance across temperature variations and component aging. They design automatic gain control systems that respond quickly to transient noise bursts without sluggish recovery that would mask subsequent weak signals. They create scale expander networks, circuits that compress dynamic range, making both strong and weak signals audible without constant manual adjustment. Test range results quantify performance improvements. Columbia and Harvard researchers conduct controlled experiments with actual submarines or submerged targets. Measurements compare detection range using earlier broadband receivers against upgraded filter-equipped systems. Representative results show several decibels improvement in signal-to-noise ratio when optimal filter settings are employed. 3 to 6 decibels sounds modest, but translates directly into range gains. The sonar range equation is logarithmic. Every 3 decibels of improved signal-to-noise ratio extends detection range by roughly 40%, assuming sound propagation remains constant. A baseline detection range of 2,000 yards becomes 2,800 yards, with 3 decibels improvement, 3,900 yards with 6 decibels. That difference, an extra 1,000 to 2,000 yards, provides critical time for convoy escorts. At convoy speed of 10 knots, an extra 1,000 yards means nearly 3 extra minutes to classify a contact, maneuver into attack position, and launch weapons before the U-boat escapes or fires torpedoes. The filter stacks move from experimental breadboards into production hardware. The JP Listening Gear series incorporates improved filtering. Later, QHB and 692 family echo ranging sets include sophisticated receiver sections with multiple filter options. Navy technical manuals begin specifying filter settings for different tactical situations. What started as laboratory curiosities becomes standard equipment and doctrine. The human factor remains critical. Filters only help if operators use them correctly. Training materials emphasize that selecting the wrong filter setting can actually degrade performance by attenuating the signal of interest. Operators learn to adjust filters based on sea state, target type, and tactical situation. A surface submarine sounds different from a submerged one. A diesel engine at cruising speed produces different tonal components than electric motors running slowly. Effective listening requires matching filter configuration to expected signature. The engineering philosophy represents a fundamental shift. Early war sonar design emphasized the active transmit cycle, powerful projectors, strong echoes, simple processing. Late war design focuses equally on the passive receive path, sensitive hydrophones, precisely shaped filters, sophisticated gain management. The ocean's physics cannot be changed. What can be changed is how carefully the receiver listens within the narrow frequency windows where submarine signals rise above natural background noise. An unintended consequence emerges during fleet trials. Some escort commanders initially resist the new equipment, complaining that filtered output sounds different or unnatural compared to familiar broadband listening. Operators accustomed to hearing all ocean noise find the filtered output too quiet, suspecting the equipment is broken. Training and experience gradually overcome this resistance. Crews discover that unnatural filtered output actually produces more confirmed detections and successful attacks. The numbers in convoy action reports begin to shift in favor of escorts with upgraded receivers and trained operators. In a convoy engagement at 12 knots, an extra 1,000 yards of detection range can mean the difference between detecting a U-boat during its attack approach or discovering it only after torpedoes strike. That extra minute or two allows coordinated response, alert other escorts, maneuver the threatened merchant ships, position an attacking escort for weapons employment. The mathematics of tactical geometry favors defenders who see the threat sooner. Filter stacks deliver that advantage, not through dramatic technological leaps, but through careful attention to what frequencies matter and what frequencies only obscure. 1943 through 1945. Sonar School, New London, Connecticut, anti-submarine warfare exercises in the Atlantic. In a darkened classroom, trainees wear headsets as an instructor adjusts a gain control knob at the teaching console. With gain set too high, the headphones roar with hiss and crackle, an overwhelming wall of noise. The instructor slowly reduces gain to the proper setting. The background noise drops. A faint rhythmic thump emerges, barely audible but distinct, the acoustic signature of a submarine propeller. Proper gain handling makes the difference between detection and nothing. Many operators initially treat the gain control as simply a volume knob. Louder is better. Division 6 studies and later papers in the Journal of the Acoustical Society of America on auditory masking show otherwise. Poor gain handling can render even improved filters ineffective. The human ear's response to sound is nonlinear. A strong noise burst can temporarily reduce sensitivity to weaker, continuous signals, a phenomenon called auditory masking. If gain is set too high, intermittent noise transients overwhelm the operator's perception, hiding the steady submarine tones that provide the only reliable detection. The technical concept of gain riding develops from this understanding. Gain riding means constant adjustment of amplifier gain to keep faint contacts just above the noise floor without saturating on transient spikes. It requires active operator participation, watching C state, adjusting gain as ship speed changes, reducing gain momentarily when a wave crash or machinery transient appears, then carefully raising gain again to recover weak signals. Done properly, gain riding extracts maximum information from marginal contacts. Done poorly or ignored, it throws away several decibels of effective signal-to-noise ratio. Engineers develop automatic solutions to support manual technique. Automatic volume control circuits and scale expander networks, documented in the summary technical reports, automatically compress dynamic range. These circuits quickly reduce gain when strong signals appear, preventing saturation, then gradually restore gain as the transient fades. Scale expanders work differently. They apply more gain to weak signals than to strong ones, effectively stretching the range of amplitudes the operator can perceive simultaneously. Both approaches aim to keep the operator's ear in its most sensitive range. The 1947 Journal of the Acoustical Society of America paper by Gales, Auditory Masking in Sonar Listening Systems, formalizes the underlying psychology. Strong masking noise reduces the ability of the listener to detect weak signals in the presence of stronger noise. The effect is frequency dependent. Noise in one frequency band primarily masks signals in nearby bands. Proper filtering helps by separating signal and noise into different frequency regions. Proper gain control helps by preventing strong transients from overwhelming the operator's auditory system. Training doctrine evolves to incorporate these findings. New London instructors teach standard gain setting procedures for different C states. Calm C, higher gain to maximize sensitivity. Moderate C, intermediate gain, adjusted frequently to manage wave noise. Rough C, lower gain to prevent constant saturation, relying more on filter selection to separate signal from noise. Operators learn scanning patterns that combine gain adjustment with frequency changes. Start at low gain, wide frequency band, then systematically narrow frequency selection and adjust gain as potential contacts are investigated. Operator manuals and training bulletins from 1943 onward emphasize that improper gain technique materially influences the range at which targets may be detected. The language deliberately echoes the summary technical report phrasing. The message is clear. Equipment improvements only deliver their potential when operators understand and apply correct procedures. A 3 decibel gain from better filters can be entirely lost if an operator sets gain 10 decibels too high and saturates on every wave. Fleet exercises provide practical validation. Anti-submarine warfare training runs compare detection statistics for crews with different levels of gain riding training. The results are consistent. Well-trained operators achieve earlier detections and longer contact duration than poorly trained crews using identical equipment. The difference often exceeds the measured hardware improvements from upgraded receivers. Technology and technique must advance together. The cumulative effect of improved circuits plus standardized gain riding procedures appears in convoy statistics. After-action reports from 1943 and 1944 increasingly note contacts held through higher C states and at longer ranges than earlier in the war. Escorts report detecting U-boats during attack approaches, not just after torpedoes strike. The time available for coordinated response increases from seconds to minutes. More U-boats are forced to break off attacks or are destroyed before reaching firing positions. The transition is not instantaneous or universal. Escort groups receive equipment upgrades and training improvements at different rates, depending on refit schedules and strategic priorities. Some groups operate with fully modernized receivers and highly trained operators by spring 1943. Others continue with earlier equipment and less sophisticated doctrine into late 1943 or early 1944. The uneven implementation creates natural comparison groups for operational researchers analyzing what works. In 1942, noisy Atlantic conditions often meant escorts reported no useful sonar contact in after-action reports. By 1944, the same sea state with trained gain riders and tuned filters yields trackable bearings on submerged U-boats. The ocean noise has not changed. The submarines have not become louder. What changed is how carefully and intelligently Allied escorts listen, filtering out irrelevant frequencies, managing gain to keep operators' ears in their most sensitive range, training crews to recognize faint, steady signals buried in transient noise. The technical improvements provide tools. The training provides the skill to use them effectively. 1943 through 1944. Western Approaches Command, Liverpool, United States Atlantic Fleet Headquarters. An operational research officer pins a new chart to the office wall. The graph displays initial contact range distributions, plotted separately for escort groups identified as having older equipment and doctrine versus those with upgraded sonar and improved listening procedures. The two curves show measurably different means. The upgraded groups detect U-boats earlier, more consistently. Before systematic measurement, commanders often attributed success or failure to intangibles: luck, weather, enemy skill, crew morale. Western Approaches. Tactical unit and operational research sections introduce quantitative evaluation, detection range, contact duration, attack success rate, convoy losses, U-boat kills. The numbers reveal patterns invisible to individual participants. The British Western Approaches Command under Admiral Sir Max Horton and United States Atlantic Fleet Headquarters both establish operational research teams analyzing convoy battles. These analysts treat anti-submarine warfare as a statistical problem amenable to measurement and improvement. They collect convoy action reports, cross-reference them with German U-boat logs captured or obtained through signals intelligence, and build databases of engagement outcomes. Key metrics include initial detection range, how far away the U-boat was when first contacted by sonar or hydrophone. This number proves critical because it determines how much time and space the escort has to develop the situation. A detection at 4,000 yards allows systematic approach, careful classification, coordination with other escorts, and deliberate weapons employment. A detection at 1,000 yards means immediate emergency response with little time for anything except dropping depth charges and hoping. The operational research teams document trends through 1943 and 1944. Escort groups equipped with upgraded sonar receivers and trained in modern listening procedures show statistically higher mean initial contact ranges. The improvement is not dramatic, often measured in hundreds of yards to perhaps 2,000 yards, but it is consistent and measurable. Kill probability per contact also improves. U-boats detected at longer range are more likely to be destroyed and less likely to escape or successfully attack. Convoy action reports provide qualitative evidence supporting the statistics. Captains mention improved echo ranging performance or clearer hydrophone bearings following refits. Reports note successful attacks launched after long tracking periods impossible earlier in the war. The language is restrained. Operational summaries avoid hyperbole. But the pattern is clear. Cross-referencing with U-boat loss data from German records confirms Allied observations. As detection ranges increase and contact duration lengthens, U-boat casualties rise. Correlation does not automatically prove causation, but the operational research analysts apply careful statistical techniques to isolate variables. They compare convoy series on similar routes with similar escort numbers but different equipment fits. They analyze how outcomes change for specific escort groups before and after refits. The data consistently points toward measurable advantages from receiver improvements and better listening doctrine. The Western Approaches operational research team, which includes scientists and mathematicians like Patrick Blackett and E.J. Williams, produces regular assessments circulated to fleet commanders and equipment committees. These reports explicitly attribute improving anti-submarine warfare effectiveness to a combination of factors: radar, high-frequency direction finding, long-range air escort, signals intelligence, and improved sonar and listening procedures. No single factor dominates. The synergy matters. United States Navy anti-submarine warfare boards conduct similar analyses. The Office of the Chief of Naval Operations maintains databases of U-boat sinkings, tracking which weapons and tactics proved most successful. Hedgehog, the ahead-throwing anti-submarine mortar that detonates only on contact, shows high kill probability when used, but requires accurate initial positioning enabled by good sonar tracking. Depth charges remain effective, but demand sustained contact to maintain position over the target. Both weapons benefit from earlier detection and longer tracking, which the improved listening systems provide. Statistical trends over the critical 12 to 18 months from mid-1942 through mid-1943 show dramatic reversal. Allied merchant ship losses peak at over 600,000 tons monthly in late 1942, then decline through 1943 despite continued U-boat numbers. Escort groups operating the same North Atlantic routes that were killing zones in 1942 show U-boat loss spikes by mid-1943, with no corresponding leap in Allied ship numbers, only better use of existing sensors and weapons. The operational researchers carefully avoid claiming that any single technical improvement won the Battle of the Atlantic. They understand that radar detection of surfaced U-boats, HF-DF location of radio transmissions, increased air escort coverage, and signals intelligence all contributed. But their statistical analyses show that sonar and listening system improvements are visible not just in laboratory performance plots, but in theater-level engagement statistics. The numbers prove that receiver-side enhancements translated into battlefield results. One particularly striking analysis compares kill-per-convoy encounter rates for different escort groups over time. Early war rates hover around 1 U-boat sunk for every 5 or 6 serious convoy attacks. By late 1943, well-equipped escort groups approach 1-to-1 ratios or better in some convoy series. The U-boat threat has not decreased. If anything, more submarines are at sea. But the probability that any given U-boat survives an encounter with upgraded escorts has fallen dramatically. The tactical balance has shifted. Post-1945, Popular Histories versus Archival Records, Technical Report Repositories. A Modern Magazine article mentions a blind engineer who accidentally tuned a sonar receiver in some unspecified laboratory, allegedly extending submarine detection range by miles overnight. The story appears in multiple retellings, each version slightly different, none providing names, dates, or locations. It carries the hallmarks of the engineering folklore: dramatic, simple, appealing. It is also unsupported by the documentary record. The anecdote suggests a single breakthrough moment, one individual, one adjustment, revolutionary results. Archival reality presents systematic, team-based, iterative work documented across hundreds of pages in the summary technical reports of Division 6 and institutional histories of wartime acoustics laboratories. No single identified blind engineer appears associated with a one-time sonar revolution in any contemporary or near-contemporary source. The summary technical reports thoroughly document contributors. Volume 14 on listening systems alone lists dozens of engineers and scientists across multiple institutions. Names appear as report authors, section editors, and principal investigators. Frederick V. Hunt at Harvard Underwater Sound Laboratory. Verno Knudsen at University of California. Division of War Research leading ambient noise studies, Maurice Ewing and J. Lamar Wurzel at Columbia, working on propagation and array theory. Chaim Pekeris contributing mathematical analysis. Many more contributors remain unnamed in the summary reports, their work appearing only as technical sections or appendices authored by institutional groups rather than individuals. Bell Telephone Laboratory's role is extensively documented. Multiple engineers contributed to filter design, automatic gain control circuits, and receiver electronics. The work proceeded through standard development cycles: concept, breadboard prototype, testing, revision, production design, manufacturing, installation, fleet trials, operational feedback, further refinement. This process took months to years, not moments. The Division 6 organization itself militates against single genius narratives. The entire structure was designed for collaborative, distributed development. Columbia specialized in theory and passive systems. Harvard focused on active sonar and transducers. California measured ocean properties. Naval Research Laboratory integrated findings into fleet requirements. Industry partners manufactured production equipment. No individual sat at the center controlling all developments. The concept of accidental discovery in this context requires careful interpretation. Scientific and engineering work routinely produces unexpected results. A test configuration might perform better than predicted. A filter design intended for one purpose might prove more valuable for another. An operator technique discovered through trial and error might later be formalized through analysis. These accidents are part of normal research and development. But they are not dramatic eureka moments. They are marginal findings that, when investigated, measured, and understood, become incremental improvements. Documented examples exist of unexpected good performance during wartime sonar development. Test ranges occasionally recorded better detection ranges with certain equipment, configurations than design calculations predicted. Investigation usually revealed that actual ocean conditions happened to favor that particular configuration, or that operator technique unconsciously optimized performance, or that some aspect of the design worked better than theory suggested. These findings were then documented, the conditions for optimal performance were characterized, and the results were incorporated into standard designs and procedures. The summary technical reports themselves demonstrate the systematic nature of the work. Volume 14 includes detailed circuit diagrams showing precisely which resistors and capacitors implement each filter stage, which vacuum tubes provide amplification, how automatic volume control functions. Performance data includes measured signal-to-noise ratios under controlled conditions, detection range test results against actual submarine targets, operator performance statistics from training exercises. This is not the documentation of a single accidental breakthrough. It is the careful compilation of incremental improvements tested and validated systematically. Range equation calculations from standard sonar texts of the period show how multiple modest improvements combine. 3 decibels from better filtering, 2 decibels from reduced self-noise, 2 decibels from improved gain control, 1 decibel from better hydrophone directivity. The improvements stack additively in the logarithmic sonar equation. Together, 8 decibels of improvement extends detection range by a factor of roughly 2.5 under favorable conditions. In practice, going from 1,800 yards to 4,500 yards, detection range represents precisely that level of combined improvement. Plausible, achievable, consistent with documented hardware changes. No magic required. If a blind engineer story has any kernel of truth, it likely represents a symbolic compression of this broader reality. Perhaps one engineer at one laboratory achieved unexpected results during a particular test. That engineer's contribution, like hundreds of others, was documented, circulated, and incorporated into standard practice. The dramatic elements, blindness suggesting special auditory sensitivity, accident suggesting unplanned discovery, miles of extended range suggesting revolutionary impact, may be narrative embellishments added after the fact to make technical history more memorable. What matters is not whether one particular engineer was blind or whether one particular test was accidental. What matters is that the Allied anti-submarine warfare effort systematically improved sonar receiver performance through organized scientific research, careful measurement, iterative engineering, and progressive fleet implementation. That systematic effort, conducted by hundreds of specialists across dozens of institutions over several years, extended detection ranges measurably and repeatedly. The achievement belongs to a community, not an individual. The method was science and engineering, not accident or intuition. The true drama lies not in a single engineer's moment of inspiration, but in the quiet accumulation of marginal gains. Filter cutoff frequencies chosen carefully. Gain laws designed based on auditory masking studies. Operator training procedures refined through feedback from fleet exercises. These unglamorous details, multiplied across hundreds of ships and thousands of convoy actions, shifted the statistical distribution of detection ranges by the critical few hundred or thousand yards that determined whether U-boats escaped or died. That is the story the archives tell. Less romantic than the blind engineer myth, more impressive for being real. Early 1943. New London, Connecticut. North Atlantic convoy escorts. In a classroom at the Sonar School, an instructor reads from a training circular dated February 1943. The document specifies new listening procedures departing from earlier doctrine. Scheduled silent periods when transmitters shut down and escorts rely entirely on passive hydrophones. Frequency band selection guidance matching filter settings to tactical situations and expected submarine signatures. Gain setting rules calibrated for different sea states. The operational paradigm is shifting from continuous echo ranging at standard settings to integrated active plus passive approaches, where tuned listening periods are central. Earlier doctrine emphasized continuous active echo ranging. Echo ranging dominated anti-submarine warfare training and tactical thinking. Hydrophone listening existed as a secondary capability, an auxiliary function used mainly when echo ranging failed or when approaching very quietly. The new doctrine reverses priorities in certain situations. Night approaches, favorable acoustic conditions, or suspected submarine presence now trigger passive listening periods as the primary detection mode, with echo ranging held in reserve to avoid alerting the target. The tactical logic draws directly from the technical developments at Division 6 laboratories. If properly configured receivers can detect submarines at ranges comparable to or exceeding echo ranging detection, and they can under the right conditions, then passive listening offers significant advantages. It reveals the escort's presence to the submarine far less clearly than active pinging. It allows detecting multiple submarines simultaneously. It conserves electrical power and reduces wear on transmitting equipment. Most importantly, it provides an additional detection channel, increasing overall probability of early contact. The training circulars standardize recommended frequency bands for different situations. Low frequency bands, below 1 kHz, for long-range detection of diesel engines and heavy machinery on surfaced or snorkeling submarines. Mid-frequency bands, 2 to 6 kHz, for propeller blade rate and reduction gear noise from submerged submarines. Higher frequency bands for close-range classification and tracking. Operators learn to start broad and narrow systematically as contacts develop, switching between frequency bands to maximize information. Gain-setting doctrine becomes explicit and prescriptive. The manuals now state directly that improper gain adjustment may reduce detection ranges materially, using language that echoes the summary technical reports. Training emphasizes that gain must be adjusted continuously as conditions change. Speed changes alter ship self-noise. Weather deterioration increases ambient noise. The operator cannot set gain once and forget it. Constant adjustment, gain riding, becomes a core competency, taught and drilled as rigorously as bearing taking or range estimation. Fleet deployment of upgraded equipment proceeds in waves through 1943. New construction escorts received the latest JP and QHB sonar sets with improved filter sections and automatic volume control from the shipyard. Older escorts receive upgrades during scheduled refits or availability periods. The installation pipeline creates cohorts, escort groups with full modernization by early 1943, others reaching that standard by summer or fall, some outliers operating older equipment into 1944. Operational research teams tracking convoy outcomes begin noting the cohort effects. Groups identified as better equipped and better trained in sonar employment show measurably different engagement statistics. The differences are not enormous. This is not a war-winning superweapon suddenly deployed, but they are consistent and accumulate across many engagements. A few percentage points better detection probability, multiplied across 50 convoy battles, produces dozens of additional U-boat sinkings and hundreds of merchant ships saved. The doctrinal shift requires cultural change in the escort fleet. Destroyer and corvette captains, many with years of experience emphasizing aggressive echo ranging and depth charge attacks, must now appreciate the value of patient, quiet listening. Sonar operators trained to focus on echo returns must develop equal proficiency with passive tonal analysis. The resistance is not universal, but it exists. Some commanders never fully embrace the new doctrine, continuing to rely primarily on familiar echo ranging tactics. Others adopt the integrated approach enthusiastically and see immediate results in improved contact rates. Training time at New London expands to cover the additional material. The sonar course now includes substantial sections on ambient noise, frequency selection, gain control, and auditory masking. Operators learn not just how to turn knobs, but why particular settings work in particular conditions. The goal is producing thinking operators who understand their equipment and can adapt to unexpected situations, not just technicians who follow rote procedures. By spring 1943, many escort groups entering the critical North Atlantic battles are operating with the new listening doctrine overlaying upgraded hardware. The tactical environment U-boat commanders encounter in these engagements differs significantly from 1942. Escorts that once echo-ranged continuously and predictably now alternate between silent listening periods and sudden targeted active searches. U-boats that once relied on the gap between escort detection and torpedo firing to ensure escape now find themselves detected and tracked from greater distances with less warning. The combination of hardware and doctrine creates synergy. Better filters only matter if operators know when and how to use them. Trained operators cannot overcome inadequate equipment. Together, improved receivers and improved procedures deliver performance neither could achieve alone. This lesson, that technology and training must advance together, will influence post-war naval development for decades. The practical impact appears in the operational statistics compiled by Western Approaches and United States Atlantic Fleet commands. By mid-1943, convoy after-action reports increasingly describe early detections, sustained tracking through rough weather, and coordinated attacks that force U-boats to abort or lead to their destruction. The escorts themselves remain the same classes: flowers, towns, rivers, destroyer escorts. Their numbers increase only moderately, but their effectiveness increases sharply. The difference lies in the black boxes bolted inside their hulls and the trained operators manning them, neither visible to external observation, both decisive in combat outcomes. May 1943, North Atlantic, Allied and German Naval Headquarters, a German naval staff officer, reviews May situation reports at U-Boat Command headquarters. The numbers are catastrophic. 41 U-boats failed to return during the month. Over 240 submarines were operationally available at the start of May. 118 were at sea. Losses approached 25% of active strength in a single month, an unsustainable casualty rate by any military standard. Allied tonnage sunk tells the inverse story. Atlantic merchant losses for May 1943 total 34 ships of approximately 134,000 gross registered tons. This figure is less than half the monthly averages of late 1942, when losses regularly exceeded 300,000 tons. The tonnage war, Germany's strategy to starve Britain by sinking ships faster than they can be replaced, has reversed. U-boats are now dying faster than they sink targets. Grand Admiral Karl Dönitz had expected spring 1943 to deliver decisive results. Through the winter, U-boat numbers at sea reached new highs. Wolfpack tactics concentrated multiple submarines against convoys. New technologies promised to restore tactical advantages. METOX radar detectors to warn of approaching aircraft, improved torpedoes with magnetic and acoustic homing capabilities. Operational planning assumed these improvements would counter Allied escorts and maintain favorable loss-to-tonnage sunk ratios. Reality delivered the opposite. The May convoy battles, ONS-5, SC-130, HX, and non-series, saw U-boat packs decimated while inflicting relatively light convoy losses. Escort groups repelled multi-submarine attacks with limited merchant losses and multiple confirmed U-boat kills. German after-action reports from surviving commanders describe effective Allied radar, aggressive air escort, and most ominously, escorts that seem to detect and track U-boats earlier and more reliably than before. ONS-5 in early May exemplifies the new dynamic. 42 merchant ships with 6 close escorts initially, reinforced by additional support groups as the battle developed. Estimates put German forces at over 30 U-boats deployed against the convoy over several days of running battles. The convoy lost 13 merchant ships, certainly serious losses, but Allied escorts sank 6 U-boats confirmed, with several more damaged. In earlier convoy battles of this scale, German forces might have sunk 20 or 30 merchants while losing 1 or 2 submarines. The exchange rate has fundamentally shifted. SC-130 demonstrates even starker reversal. 38 merchant ships with 7 escorts face concentrated U-boat attacks in mid-May. The convoy reaches port without losing a single merchant ship. 3 U-boats are destroyed, several others damaged and forced to withdraw. For the attacking U-boat force, SC-130 represents complete tactical failure. No target sunk, significant losses sustained. Convoy action reports from Allied commands note the pattern. Escorts detect attacking U-boats during their approach phases, often at ranges of 3,000 to 4,000 yards, in conditions that previously yielded no contacts. Sustained sonar tracking allows coordinated attacks using hedgehog ahead-throwing weapons or precisely placed depth charge patterns. Air escorts, now equipped with centimetric radar and increasingly available through extended range and escort carrier deployment, catch U-boats attempting to surface or transit on the surface. The multiple factors interact synergistically. HF-DF bearings cue escorts toward U-boat radio transmissions, then sonar or radar completes the detection and allows attack. Air radar spots surfaced submarines, forcing them to dive, where improved underwater detection picks them up. Signals intelligence routes convoys away from known U-boat concentrations, but when contact occurs, escorts possess tools to fight effectively. No single factor dominates. The system-level superiority proves overwhelming. German assessments struggle to identify the key Allied advantage. Reports mention improved Allied radar frequently. It has become much harder to surface undetected. Air coverage receives blame. U-boats can no longer safely operate on the surface, even in mid-ocean. Tactical discussions note that British escort groups seem better coordinated and more aggressive, but the reports rarely highlight improved underwater detection explicitly because German intelligence cannot directly observe receiver-side improvements in Allied sonar. They see the results, earlier detections, longer tracking, more successful attacks, without clearly understanding the causes. Post-war analysis by German naval historians confirms the May 1943 disaster. Over 200 submarines are destroyed in calendar year 1943, with May representing the peak crisis. Another 245 go down in 1944. Meanwhile, Allied shipping losses trend steadily downward. New ship construction far exceeds losses from summer 1943 onward. The strategic balance has irreversibly shifted. Dönitz responds to the May losses by temporarily withdrawing U-boats from the North Atlantic convoy routes. The decision tacitly acknowledges defeat in the primary campaign. U-boats redeploy to secondary theaters where Allied defenses are weaker: the South Atlantic, Indian Ocean, Mediterranean. Later, 1943 sees renewed North Atlantic operations as new U-boat technologies, snorkels, improved acoustic torpedoes, promise to redress Allied advantages. But the concentrated Wolfpack campaigns that nearly severed Atlantic supply lines in 1942 never resume at the same scale or effectiveness. British and American operational research reports assess the turning point with clinical precision. The summary report on anti-submarine warfare published post-war describes spring 1943 as exhibiting a complete reversal of fortunes in the Atlantic campaign. Merchant losses decline while U-boat losses surge. The assessment attributes the change to the convergence of technology, tactics, and intelligence, explicitly listing improved sonar and listening procedures among the decisive technologies alongside radar, HFDF, air escort, and signals intelligence. The statistics of Black May, 41 U-boats destroyed, merchant losses cut by more than half, cannot be explained by any single innovation. But when operational research models incorporate measured improvements in sonar detection range and tracking duration, they account for significant portions of the observed changes in engagement outcomes. Extended detection ranges translate into more time for coordinated attacks, higher weapon employment success rates, and reduced probability of U-boats reaching firing positions. The quantitative models confirm what convoy commanders experienced: better sonar made escorts more lethal and convoys more survivable. From summer 1943 onward, U-boats never regained strategic initiative in the North Atlantic. They remain dangerous, individual attacks continue, and losses occur through the end of the war. But the existential threat to British survival and Allied logistics is broken. The sea lanes remain open for the massive buildup of forces and supplies leading to D-Day in June 1944. The Battle of the Atlantic, the longest campaign of the European War, turns decisively in the Allies' favor. And hidden among the multiple contributing factors lie retuned filters and disciplined gainwriting that extended detection ranges by those critical few thousand yards. 1943 through 1946. Anti-Submarine Warfare Research Offices, compilation of Division 6, Summary Technical Reports. Post-war researchers assemble comparative graphs showing detection range versus sea state for older versus upgraded listening systems. The data comes from wartime trials and convoy operational statistics. The plots show measurable, repeatable improvements. A few decibels of signal-to-noise ratio, translating into hundreds to a few thousand yards of extended practical detection range under favorable conditions. Popular narratives of the Battle of the Atlantic emphasize dramatic technologies: radar finding surfaced U-boats, aircraft sinking submarines caught on the surface, code breakers revealing convoy routing. These contributions were real and important. Technical reports reveal an additional factor: modest, cumulative gains in receiver performance that played a measurable, repeatable role in convoy defense. The sonar range equation provides the mathematical framework. Detection range depends on source level, transmission loss, ambient noise, and receiver sensitivity. Source level, how loud the target is, cannot be controlled by the escort. Transmission loss, sound absorption and spreading in seawater, is determined by physics and ocean conditions. Ambient noise comes from wind, waves, and biology. The only variable fully under Allied control is receiver sensitivity: how much signal-to-noise ratio the receiver can extract from the returning acoustic energy. Representative figures from summary technical report data show typical improvements. Under moderate sea conditions, Sea State 3, common in the North Atlantic, optimized filter stacks and gain procedures extended practical detection range by approximately 20 to 30% compared to earlier broadband systems. In some favorable conditions with trained operators, improvements reached 40 to 50%. A baseline 2,000-yard detection range becomes 2,400 to 3,000 yards. A 3,500-yard detection becomes 4,200 to 4,800 yards. Not revolutionary, significant. The tactical geometry makes those extra hundreds or thousands of yards critical. At convoy speed of 10 knots, 1,000 extra yards of detection range provides roughly 3 additional minutes of warning and reaction time. 3 minutes allows an escort to alert the convoy, signal other escorts, begin maneuvering into attack position, and classify the contact before weapons employment becomes necessary. Without that margin, the first indication of U-boat presence may be torpedoes in the water. Operational probability models used by Western Approach's operational research teams quantify the effect. Early detection creates multiple tactical advantages. More time allows better classification, reducing false alarms and wasted depth charges. Extended tracking provides better position estimates, improving weapon accuracy. Longer engagement times permit coordinated attacks by multiple escorts, increasing kill probability. The models show how incremental detection range improvements translate into measurably higher U-boat loss rates and lower convoy casualties. Specific convoy comparisons illustrate the system-level impact. Consider 2 notional convoys on similar routes with similar escort numbers. Convoy A has escorts with earlier standard sonar. Mean initial detection range, 1,800 yards. Convoy B has escorts with upgraded receivers and trained operators. Mean initial detection range, 3,000 yards. In Convoy A engagements, U-boats often reach firing positions before being effectively countered. In Convoy B engagements, escorts more often detect and engage U-boats before they can optimally position for attack. Convoy B suffers lower merchant losses and inflicts higher U-boat casualties. The difference, 1,200 yards of mean detection range, makes the convoy a significantly harder target. The summary technical reports present these gains as engineering achievements measured under controlled conditions. Test ranges used actual submarines or realistic targets at known positions. Hydrophone systems with known characteristics were tested under documented sea states. Detection ranges were measured multiple times and averaged. Statistical analysis confirmed that improved filter configurations and gain procedures produced consistent advantages. This is empirical data, not speculation. Translation from test range to operational statistics involves uncertainty. Combat conditions vary more than test conditions. Operator fatigue, equipment maintenance, tactical stress, and unpredictable ocean properties all affect real-world performance. But the statistical distributions from convoy action reports match the test range predictions. Escorts with upgraded equipment show detection range distributions shifted toward longer ranges by amounts consistent with laboratory measurements. The field data confirms the lab results. The operational research conclusion is clear, though understated. Improvements in radar, HFDF, air escort, signals intelligence, and underwater detection collectively reversed the Battle of the Atlantic. No single factor was decisive. No single factor was dispensable. The system worked because all elements improved together. But within that system, the sonar and listening equipment improvements are quantifiable, documented, and demonstrably effective. Typical OR assessment language notes that tactical and technical improvements combine to increase U-boat loss rates while reducing convoy casualties. The phrase deliberately avoids assigning precise credit to individual factors, but the underlying models include detection range as an explicit parameter. When detection range increases in the model by amounts measured in laboratory and field tests, predicted outcomes match observed convoy statistics. The mathematics confirms the hardware improvements mattered. One striking comparison appears in German post-war assessments. German analysts reviewing their 1942 successes versus 1943 failures consistently note that Allied escorts seemed to know where U-boats were more reliably by mid-1943. German intelligence correctly identified improved Allied radar, increased air patrols, and suspected code breaking as contributors. They noted better Allied escort tactics and coordination. But they missed the receiver-side sonar improvements because those changes were invisible from outside the escort ships. Germany could observe that Allied escorts detected U-boats more effectively. They could not easily determine why. The irony is profound. Germany invested heavily in U-boat technology through the war, improved torpedoes, snorkels, Type 21 high-speed submarines, better sonar detection of escorts. These developments came too late or in too small numbers to affect outcomes. Allied sonar improvements were neither glamorous nor expensive. Filter networks cost hundreds of dollars per installation. Training updates required printing new manuals. The effect was cumulative and distributed across hundreds of ships. By the time Germany realized Allied underwater detection had improved substantially, the Battle of the Atlantic was already lost. Post-war examination of captured German equipment showed that German hydrophone and sonar technology was often comparable to Allied hardware. The difference lay not in the transducers, but in the receiver chains and operator training. German listening systems used relatively broadband amplification without the sophisticated filtering and automatic gain control developed by Division 6 laboratories. German operator training emphasized echo ranging over passive listening. Small differences in approach, multiplied across thousands of engagements, produced large differences in outcomes. The documented range gains, a few decibels, hundreds to a few thousand yards, represent the engineering reality behind Black May and the subsequent U-boat defeat. On paper, incremental. In the logbooks, decisive. In the final accounting, hundreds of U-boats that did not return, thousands of merchant seamen who survived, millions of tons of supplies that reached Britain to sustain the war effort. The margin of victory measured in filter cutoff frequencies and gain law, coefficients carefully tuned by engineers who never went to sea. 1945 through 1950. New London, Connecticut. Transition to Naval Underwater Sound Laboratory. Early Cold War sonar development. Wartime laboratories close or transform. Harvard Underwater Sound Laboratory equipment moves to New London. Columbia University Division of War Research staff disperses to permanent Navy research establishments or returns to academia. The university-based wartime collaboration formally ends, but the expertise, methods, and lessons persist, directly shaping the next generation of undersea warfare systems. Many veterans expect sonar research to wind down after 1945. With U-boats defeated and no immediate submarine threat visible, investment in anti-submarine warfare might logically decline. Instead, the opposite occurs. Wartime experience convinced Navy leadership that receiver-side sophistication would be central to future undersea warfare. The emerging Cold War, with Soviet submarine forces inheriting German technology and expanding rapidly, demands continued development. The Naval Underwater Sound Laboratory consolidates scattered wartime capabilities into a permanent institution. The facility at New London absorbs personnel, equipment, and accumulated knowledge from Harvard, Columbia, and other wartime sites. The transition preserves institutional continuity. Engineers who designed filter networks and gain laws during the war continue working on the next generation of systems. The accumulated expertise is not lost with demobilization. Declassification and internal distribution of Division 6 summary technical reports provides essential reference material. The Red Books, bound volumes with distinctive covers, become standard references for new sonar designs. Engineers working on post-war projects routinely consult Volume 14 on listening systems, Volume 10 on echo ranging equipment, and related technical reports documenting wartime findings. The knowledge base is preserved and made available. Post-war shipboard sonars incorporate wartime lessons directly. More complex filter banks allow finer frequency discrimination. Improved automatic gain control responds faster and more accurately. Beamforming techniques using multi-element arrays sharpen directivity. And eventually, digital signal processing begins replacing analog circuits, but the fundamental principles remain rooted in Division 6 work. Shape frequency response to match target signatures, manage gain to optimize auditory perception, train operators to understand what they hear and why. The most dramatic application of wartime listening system principles appears in SOSUS, the Sound Surveillance System. Beginning in the early 1950s, the Navy installs bottom-mounted hydrophone arrays at strategic ocean locations to detect Soviet submarines transiting between bases and patrol areas. SOSUS relies entirely on passive listening. There is no active transmission. Success depends on receiver sophistication, array design, filtering, noise reduction, signal processing. Every element traces lineage to Division 6 wartime research. SOSUS array designs use concepts developed at Columbia for wartime passive detection systems. Filter networks draw on Bell Labs circuit designs refined for World War II listening sets. Ambient noise characterization comes from UCDWR measurements, extended and updated. Operator training incorporates auditory psychology lessons learned during the Battle of the Atlantic. SOSUS represents the ultimate expression of the philosophy that listening carefully matters more than transmitting loudly. Cold War submarine detection doctrine emphasizes stealth and passive operation. Surface ships increasingly rely on towed arrays, long lines of hydrophones streaming behind the ship, to maximize sensitivity and directionality while minimizing self-noise. Submarines hunt each other primarily with passive sonar, avoiding active transmission that reveals position. The technological contest becomes explicitly about who can hear quietest signatures against ambient noise, exactly the problem Division 6 addressed 15 years earlier in a different context. Soviet submarine technology develops along a parallel but distinct path. Soviet forces inherit German-type Variant technology and develop increasingly capable submarines through the Cold War. But Soviet emphasis remains on speed, depth, and weapon systems, more than acoustic stealth. Later, Cold War assessments suggest Soviet submarines were generally noisier than American boats, making them more vulnerable to passive detection, despite being otherwise formidable. The technological choices made during World War II echo forward for decades. Training standards institutionalized during 1943 through 1945 become permanent Navy doctrine. Sonar operator schools continue, emphasizing gain riding, frequency selection, auditory discrimination, and systematic search procedures. The wartime discoveries about auditory masking, operator fatigue effects, and optimal training methods are incorporated into formal curriculum. Post-war operators learn techniques developed under combat pressure in the North Atlantic. The archival record documents explicit continuity. Post-war Navy technical histories cite Division 6 reports as foundation documents for Cold War sonar development. Engineers writing in professional journals reference wartime findings as baseline knowledge. The Journal of the Acoustical Society of America publishes declassified wartime research in the late 1940s and early 1950s, making it available to the broader scientific community. The knowledge diffuses but remains rooted in the urgent problem-solving of 1942 through 1945. One profound lesson carries forward: incremental, systematic improvement defeats dramatic but delayed innovation. Germany's type, Gedeofen submarine and advanced acoustic torpedoes, represented technological leaps, but arrived too late and in too few numbers. Allied receiver improvements were modest individually, but deployed quickly and broadly. The side that got workable solutions into the field first, then continuously refined them, prevailed over the side that pursued perfection but achieved it too slowly. The organizational lesson also endures. The Division 6 model of coordinated university-Navy-industry collaboration with clear problem definitions and rapid feedback from operational experience proved highly effective. Post-war defense research adopts similar structures: university laboratories under contract, close liaison with operational commands, systematic documentation, and knowledge transfer. The wartime experience validated methods that become standard practice. By the early 1950s, the decisive contest in undersea warfare has shifted firmly to who can listen best. Surface ships and submarines alike invest heavily in receiver systems, more sensitive hydrophones, more sophisticated processing, better noise isolation, advanced beamforming. Active sonar remains important for specific tasks: torpedo homing, mine hunting, close-range detection, but long-range submarine detection becomes primarily a passive listening problem. The technological trajectory begun in the North Atlantic in 1943 leads directly to Cold War emphasis on acoustic stealth and sensitivity. The engineers and scientists who fought the acoustic battle of World War II established principles that governed undersea warfare for the rest of the 20th century. Filter design, gain management, frequency selection, auditory psychology, operator training, the fundamentals developed under wartime pressure, remained relevant through decades of technological change. Digital replaced analog, but the sonar equation still balanced source, propagation, noise, and receiver. Physics did not change. The question remained how carefully and intelligently systems could listen through ocean noise to hear faint signals that mattered. 1939 through 1945. Summary. Post-war assessments in London and Washington. A final summary table lies on a historian's desk, documenting the cost of the longest campaign of World War II. 3,500 Allied merchant ships lost to U-boats. 175 Allied warships sunk. 783 U-boats destroyed. 72,000 Allied naval and merchant seamen killed. 30,000 German submariners dead, 3/4 of all who served in U-boats. The Battle of the Atlantic consumed lives and materiel on an industrial scale. Germany's strategic expectation was simple: sink ships faster than they could be replaced, starve Britain, force surrender, or negotiated peace before American industrial power could fully deploy. The tonnage war followed brutal mathematics. Each merchant ship represented cargo capacity. Each cargo represented sustenance for Britain's population and war machine. Systematic destruction of shipping at rates exceeding replacement would inevitably achieve German objectives, regardless of other military developments. The final outcome inverted German expectations. Britain survived. Atlantic sea lanes remained open. The massive buildup of American and Canadian forces and supplies necessary for D-Day and the liberation of Europe proceeded on schedule. U-boats suffered unsustainable losses, culminating in strategic defeat by mid-1943, despite continued operations through 1945. The tonnage war was lost decisively. The statistical turning point is clearly visible. Monthly Allied merchant losses peaked in late 1942 at over 600,000 gross registered tons. By summer 1943, losses fell below 200,000 tons monthly, despite similar or greater U-boat numbers at sea. U-boat losses accelerated. Over 200 submarines destroyed in 1943, 245 more in 1944. The curves cross unmistakably. After May 1943, Germany is losing the battle at an accelerating rate. Multiple factors contributed to the reversal. High-frequency direction finding allowed locating U-boats from their radio transmissions. Centimetric radar detected surfaced submarines day and night. Long-range aircraft closed the mid-ocean air gap, covering convoys throughout their Atlantic crossing. Escort carriers brought air support directly to threatened convoys. Signals intelligence provided warning of U-boat patrol lines and pack concentrations. Increased escort numbers allowed more comprehensive convoy protection. Better tactics improved coordination and attack effectiveness. And underwater detection, sonar, and passive listening extended effective ranges and improved tracking reliability. The summary technical reports, operational research assessments, and post-war official histories explicitly include improved sonar among the decisive technologies. Not the most glamorous factor, not the only factor, but a documented, measured, repeatable contributor to Allied success. The quantitative evidence is compelling. Detection range improvements of several hundred to a few thousand yards, achieved through filter optimization and gain management, appear consistently in both test data and operational statistics. These improvements translate directly into higher contact probability, longer tracking duration, more successful attacks, and ultimately lower convoy losses combined with higher U-boat casualties. The sonar equation links hardware performance to tactical outcomes, and tactical outcomes aggregate to strategic results. The human cost demands respect and remembrance. Merchant seamen sailed knowing every voyage might be their last. U-boat crews endured claustrophobic conditions and faced extraordinarily high casualty rates. Escort sailors spent years at sea under brutal North Atlantic conditions, hunting an often invisible enemy. The technology and tactics ultimately determined who won, but individual courage and sacrifice characterized both sides throughout. The archival record supports systematic, data-driven refinement of sonar receiver performance across multiple laboratories and navies, not a single heroic breakthrough. Hundreds of engineers, physicists, and acousticians contributed to incrementally improving filters, gain circuits, and operator procedures. Thousands of escort crews implemented those improvements in combat, learning through experience what worked and feeding lessons back to developers. Tens of thousands of convoy sailors benefited from detection range extensions they never saw or understood. The blind engineer story, whether true in specific detail or mythic embellishment, serves as useful shorthand for a complex reality. Someone at some laboratory probably did achieve unexpected results through a particular test configuration. That finding, like hundreds of others, was documented, validated, and incorporated into fleet systems. The dramatic narrative elements, blindness suggesting special ability, accident suggesting unplanned discovery, miles of range extension suggesting revolutionary impact, compress years of distributed effort into memorable form. But the real achievement belongs to the systematic method, not to individual inspiration. The Office of Scientific Research and Development created a networked structure linking universities, Navy laboratories, and industry. The structure enabled rapid problem identification, distributed solution development, systematic testing, and fleet-wide implementation. Problems discovered in convoy battles reached laboratory benches within weeks. Solutions tested on ranges deployed to operational ships within months. Feedback loops closed quickly enough to affect ongoing campaigns. That organizational and methodological achievement proved as important as any specific technical advance. The Allied ability to identify problems, develop solutions, test them, deploy them, and refine them based on operational experience outpaced Axis efforts despite significant German technical competence. Speed of the innovation cycle mattered as much as brilliance of individual innovations. The Battle of the Atlantic was won through convergence: radar, HF, DF, air escort, signals intelligence, tactics, training, logistics, industrial production, and underwater detection, all improving simultaneously and synergistically. Remove any major factor and outcomes might have differed, but the historical record, documented in technical reports, operational research assessments, convoy statistics, and U-boat loss data, confirms that improved underwater listening systems contributed measurably to victory. In the North Atlantic from 1939 through 1945, the decisive edge often lay not in louder pings, but in the ability to hear a fraction of a decibel more clearly than the enemy expected. A few thousand yards of extra detection range, achieved through carefully tuned filters, disciplined gainwriting, and trained operators, translated into convoy sailors reaching port alive and U-boats not returning to base. Technology at the scale of resistor values and capacitor specifications, aggregated across thousands of engagements, shifted strategic outcomes. That is what the archives document. That is what the numbers prove. That is how wars are won, not through miracles, but through meticulous accumulation of marginal advantages until the margin becomes decisive.